This is the problem for the car engine. I couldn't find any better diagram, so I'm just using this one there. And it says, suppose the gasoline in a car engine burns at 631 degrees Celsius, while the exhaust temperature of the cold reservoir is 139 degrees Celsius, and the outdoor temperature is 27 degrees Celsius. Assume that the engine can be treated as a Carnot engine, a gross oversimplification, and I mentioned that earlier. Why we're doing that? Because the equation becomes rather simple for the efficiency. In an attempt to increase mileage performance, an inventor builds a second engine that functions between the exhaust and outdoor temperatures and uses the exhaust heat to produce additional work. Assume that the inventor's engine can also be treated as a Carnot engine. Determine the ratio of the total work produced by both engines to that produced by the first engine alone. Now, one could say, well, why isn't there such a thing? Well, probably building such a second engine would kind of double the space needed for these two engines in a car in order to increase efficiency, and then you have more weight and you have more maintenance and so on. Okay, third time might be a charm. This is actually my third take on this one. I first made a mistake. I'll show you in a moment, and then I made another mistake of slightly unplugging the microphone, so my second take, which was the corrected version, was mute. So I'm actually not writing at this point, I'm just taping over my already recorded recording. And so what we have sitting here is the high temperature is given for the first engine, the cold temperature is given for the first engine. We're supposed to figure out what the efficiency is for that first engine. And then the high temperature for the second engine is given, and by the way, that should actually read E2 there, the question mark. I guess I forgot that entirely. And then the high temperature for that second engine is the temperature of the rejected heat from the first engine. That's why it's also called TC, and then its low temperature is TA. And so here I continue with my kind of muted recording, and then all of a sudden it jumps to something there because I've already written it down. There we go. And what I'm saying here is, here's what I first wrote down here is what they actually want to know is the ratio of the total work of the two engines together, so work 1 plus work 2, the ratio of that to the work of the first engine just by itself, and that's why I wrote question mark. Then I wrote down the efficiency for the first engine as 1 minus TH over TC, but that's the actual mistake I made. And then I just kept going and noticed that later on, oh wow, at the very beginning I made this mistake, and so here I believe I'm about to erase that, and of course it's supposed to say that the efficiency of the first engine is 1 minus TC over TH, the cold temperature over the high temperature. And when you plug in the numbers, you have to say that the cold temperature is not the 139 degrees Celsius, but you have to convert that to kelvins, so 412 kelvins, and then the high temperature is not 631 degrees Celsius, but 904 kelvins, and you plug those numbers in and you can write them as a decimal or a percentage. But either way you do it, it's probably better to write it down as a decimal because you will need it later. That's why I pointed at the work equation up there. For E2, the efficiency E2 would be the 1 minus the colder temperature, which is the air temperature, minus the TC, which is the high temperature for the second engine and used to be the cold temperature from the first engine. And again, that's the rejected heat that goes into the second engine. Again, that comes out to a decimal or a percentage. So the air temperature is not 27 degrees Celsius, but 300 kelvins is what you have to plug in. And of course, for the TC, again, you have to plug in 412 kelvins. So you come up with decimals for both of these efficiencies. Okay, let's see what's going to happen next. I'm not exactly sure why I pointed these here. So probably because I'm kind of describing here it over the muted microphone. And of course I can't repeat myself verbatim throughout the entire problem. I'm going to give myself a little bit of time here, and I think the next thing I'm going to do is I'm going to pull down that equation W1 plus W2 over W1. So there we go. And now I'm going to see what else I have. And the book also says that I can calculate the efficiency if I know what the work is and the input heat, and write it as work equals efficiency times the input heat. However, I don't know that input heat, but we'll see that it'll work, that once I actually plug these in here, that we will come up with a result. Okay, now for W2 I'm going to do something similar, and the work 2 of for the second engine is the efficiency of the second engine, and again in the very top right corner it should say E2, not just E. So efficiency of the second engine times the heat input to the second engine, which is the rejected heat from the first engine, so that's why I can write QC. Now I substitute all of that into that W1 plus W2 over W1 and come up with this expression. Again, from my very first take, I had that already prepared, so I'm plugging it in. There it is. And I'm looking at two terms divided by the denominator. And what these two terms here doing is, so as I divide the first term by the denominator, of course that's the same, so I come up with 1, and that kind of justifies that I can actually use these unknown QH and QC because they seem to divide out. Now I look at the second term, QC over QH, and I notice that I also got an equation for that, which is that the efficiency equals 1 minus QC over QH, which is the same for all engines. And I'll correct it in a moment. I will put a C there on the numerator for the QC. There it is. Okay, so now I'm going to plug that in there. First of all, I'm going to have, I guess I'm going to say again that these two are 1, and then on the second one it's E2 over E1. And now I'm going to plug in QC over QH for the first engine, which when you look at it is 1 minus the efficiency. And because this is about the first engine here with the QC QH1, that must be 1 minus the efficiency of the first engine. And then that equals, so, and then here I'm explaining, well, this is why I was able to use these heat flows even though I don't know them, because at the end they divide out anyway because of that extra equation that I had, the 1 minus QC over QH. I was able to manipulate in such a way that they actually divide out, and all I have in my final equation is known variables that I calculated earlier. And then that of course equals some kind of ratio. It's going to be in the neighborhood of like 20% higher, so the second engine produces 20% more work than the first engine.